In this video, we're going to learn about a way to use a subgroup of a group to divide that group into a bunch of disjoint pieces, so pieces having nothing in common, all of which have the same size. And this is going to be useful both because these pieces, which are called cosets, are interesting in their own right, and also because of the interesting numerical condition it implies for the size of a subgroup of a given finite group. So let's begin with the definition of a coset. And in fact, we have two different types of cosets, left and right cosets. But they both start in the same place, which is that we take a group G, an element X of G, and a subgroup H of G. We then define the left coset X times H to be the set of all things you can get by multiplying an element of H on the left by X. Similarly, the right coset H times X is defined to be the set of all things that you can get by multiplying an element of H on the right by X. There's then some notation for the set of all cosets. So the notation is G colon H for the set of all left cosets of H in G. This might look slightly strange, but we're stuck with it by tradition. This is the universal notation for the collection of cosets, or nearly universal. And H colon G means the set of all right cosets of H in G. Let's look at some example cosets now, and we'll begin with an example using the symmetric group. We take H to be the cyclic subgroup of S3 generated by the 2-cycle 1, 2. Now, since a 2-cycle has order 2, that cyclic subgroup has size 2, and the things it contains are the identity element and the 2-cycle 1, 2 itself. We're going to work out some of the left and right cosets of H in S3. And let's begin with the simplest of all, which is the left and right cosets of the identity. And I claim that the left and right cosets of the identity are just H again. The reason for that is if you think of the definition of the left coset of H by the identity, what that means is all things of the form identity multiplied by H for H in H. But of course, when you multiply by the identity, you don't change this H. So what you get is a set of all things H, where H is in H, which is just a strange way to write the subgroup H again. And similarly for the right coset as well. So our first bullet point just tells us that the left or right coset by the identity is the same as the subgroup H again. We'll look at another example now, so a coset by the element 1, 2. So again, we can work this out just using the definition. Let's look at the left coset of H by 1, 2. So what that would be the set of all things you can get by multiplying an element of the subgroup H on the left by 1, 2. So there are only two things in this subgroup H, which are the identity and 1, 2. So this should consist of 1, 2 times the identity and 1, 2 times 1, 2. But of course, what you've got there is just 1, 2 and the identity, and that is H again. So the left coset of H by 1, 2 is H again, and similarly the right coset of H by 1, 2 is H again. So moving on to a more interesting example, let's look at the left coset by the 3-cycle 1, 2, 3. So by definition, that is the set of all things you can get by multiplying 1, 2, 3 into an element of H. So we should get 1, 2, 3 times the identity, which is 1, 2, 3 again. And we should get 1, 2, 3 times 1, 2, which is 1, 3. So the left coset of H by 1, 2, 3 is the set containing 1, 2, 3 and 1, 3. On the other hand, if we look at the right coset of H by 1, 2, 3, well then we get the identity times 1, 2, 3 and 1, 2 times 1, 2, 3. And if you do that second multiplication right here, then what you'll get is 1, 2, 3 and 2, 3. So you can see that these two things are different. The left coset by 1, 2, 3 is different to the right coset by 1, 2, 3. As here they are, one of them contains 1, 3, one of them contains 2, 3. They're different. Okay, some other examples. Let's work out left cosets by 2, 3. Well, if you do this, then what you get at the end is 2, 3 and then 1, 3, 2. And here is an interesting observation, which is that if you worked out the left coset by 1, 3, 2, you would also get the same answer. And if we look at the right coset h23, then you get 2, 3, and 1, 2, 3. And that is the same as the right coset of h by 1, 2, 3. Okay, so just look at this. That was the right coset of h by 1, 2, 3. What consisted of 1, 2, 3 and 2, 3. And you can see it's exactly the same as what we've got here. So this gives us an interesting observation, which is that two cosets can be equal even when they are cosets by different group elements. So we're going to add this as a comment at the bottom because it's super important. So let's notice we can have GH equals KH or HG equals KG, even if G is not equal to K. Of course, I meant HK there. Even if G is not equal to K. So we've just seen an example of that happening. So this raises an interesting question, which is, when are two cosets equal? So they don't have to have the same label. So what condition can we give on two group elements for them to have the same left coset of a subgroup H or the same right coset of a subgroup H? So we're going to come to an answer to that question shortly, but I'd like to show you some more cosets to show that they often have a useful and interesting interpretation. So we're going to think about the additive group of integers. So when we just write z on its own without specifying the operation, it always means the group of integers under addition. There's no other natural operation making z into a group. So when we don't specify the operation, it means the operation of addition. Now if we take nz to be the set of all integer multiples of m, then nz is a subgroup of z. You're going to prove that in your unassessed coursework 5. Now in an additive group, you often use a slightly different notation for cosets. Writing xh would look a bit strange because we're not multiplying things, we're adding them in an additive group. So we'll write x plus h to mean the left coset of h by x. And so what that will mean is the set of all things of the form x plus h for little h in big H. So let's think what these cosets will look like then. We'll think of the coset 0 plus nz. Well, of course, that's just nz again. We've already seen this property for subgroups of the symmetric group on the last slide. But more interestingly, what if we look at the left coset 1 plus nz? So that's all things of the form 1 plus a multiple of n. In other words, it's all integers with remainder 1 when you divide by n, because those are the things which differ by a multiple of n, differ by 1 from a multiple of n. So this is something we've met before. This is a congruence class of 1 modulo n. And similarly, if you look at 2 plus nz, that consists of all things of the form 2 plus a multiple of n. In other words, all the integers with remainder 2 when you divide by n. So this time what you have is the congruence class of 2 modulo n. Again, on unassessed coursework 5, you're going to prove that this thing holds in general, that these congruence classes are actually cosets of a subgroup nz. Okay, so this illustrates that cosets are often things which we were interested in for independent reasons. So studying cosets can help us shed light on things which we were already interested in. Let's come back to this point I was making before about when are two cosets equal. So we'll prove that if H is a subgroup of G and X and Y are elements of G, then the two cosets XH and YH are equal if and only if Y inverse times X is in H, and a similar result for right cosets. So I will prove the result for left cosets, and I will leave the right coset one, which is, of course, very similar to U. So this is an if and only if statement, so we have to do two directions. So let's first of all suppose that XH is equal to YH. And we're then going to prove that y inverse times x is an element of H. So then, what can I say? I can say that x is an element of xh, because x, it's certainly equal to x times the identity element, which I will write with an e as usual. And h is a subgroup, so it contains the identity element. So this x times e is an element of xh, and that's equal to yh. So if x is an element of yh, x must be equal to y times an element of h. So let's say y times k for some k in h. Okay, now we just have to rearrange this a little bit. So if I multiply that equation on the left by y inverse, I multiply both sides by y inverse, then on the left I get y inverse x. On the right, y inverse cancels out the y, and I just get k, which was an element of h. So we've proved if those two cosets were equal, then y inverse times x is an element of h. So we've done the first implication. Now we've got to do the other implication. So let's suppose that y inverse x is an element of h, and I have to prove that the two cosets xh and yh are equal. So we'll do it with a double inclusion. We'll show that every element of xh is in yh and every element of yh is in xh. So let's, as our first step then, let's take an element of xh and prove that it is in yh. So what can I do? xh is equal to y inverse xh. Okay, I've just put in a factor of the identity, and of course multiplying by the identity does nothing. And this we can rewrite as y times y inverse x times h. Okay, now I want to convince you that that thing in the brackets is an element of the subgroup capital H. So the reason that that's true is that this thing here, those first two terms in the product, that is definitely an element of H, because this is how we're assuming in this direction. And also the second thing, little h, that is an element of H, because we took an element, x times little h, in the left coset, x times capital H. So there you've got two things in H multiplied together. But H is a subgroup, so the product of two things in H is in H again. So this is in YH because it is an element of Y times an element of the subgroup capital H. Okay, what we've shown then is every element in the coset XH is in the coset YH. So we've shown that the coset XH is a subset of YH. So let's now do the other way round. So we're going to let little y times h be an element of YH, and we're going to prove that actually this thing is also in XH. So we try and do the same thing. So YH is equal to x to the minus 1 YH. Okay, and again we're going to bracket it up. That's x times x to the minus 1 y times h. And I'd like to do the same argument, but I'm a little bit stuck. I mean, this lowercase h here, for sure that's an element of h. But x inverse y, well, I don't yet know that that's in h. But what we can do is just notice that it is the inverse of y inverse x. So y inverse x was an element of h. So let's start by saying this. Y inverse x, this is what we were assuming when we were doing this direction. That's in h. So its inverse is also in h, because h is a subgroup, so it's closed under taking inverses. But in any group, just like we proved for matrices, just like we proved for permutations, the inverse of a product AB is always equal to B to the minus 1, A to the minus 1, and the inverse of A to the minus 1 is A. So those things are always true in any group for the same reasons that they were true for matrices and the same reasons they were true for permutations. So y inverse x to the minus 1 is x to the minus 1 times y inverse inverse, which is just y again. Okay, so going back to our string of equations, yh was equal to x times x to the minus 1y times h, and we've established that this part is in h and this part is in h. So because h is a subgroup, it is closed under multiplication, so that thing in brackets is also in h, so this whole thing is in xh. So what have we done? We've shown that xh is contained in yh, and we've shown that yh is contained in xh, so xh equals yh. Okay, we've done the other direction of our proof now, so we're done. And we now know precisely when two left cosets of a given subgroup are equal. They're equal if and only if the condition in the lemma holds. This lemma is going to be referred to, in fact referred to several times, by the name the coset equality lemma, because it tells you when two cosets are equal. So here's another result which is going to be useful to us. It tells you that any two cosets are either equal or they're disjoint. That means they intersect in the empty set. They don't have any elements in common. So the way we're phrasing this is by saying that if they have an element in common, then they must be equal. So let's do this. We'll now try and do the proof of this result. So we have to suppose that these two cosets have an element in common, that they don't intersect in the empty set, and prove that they're equal. So we'll suppose that xh intersect yh is not the identity. Sorry, not the empty set. So it contains an element. It contains an element of G. So there exists a group element Z which is in xh intersect yh. Then Z, well, it's in the left coset xh, so it's equal to x times h for some little h in h, and it's also equal to y times k for some k in h. So xh equals yk, and we're going to multiply this on the left by y inverse. I get y inverse hx equals, well, I cancel out the y on the right hand side of the equation and I just get k. Okay, that looks a bit like the coset equality condition from our previous lemma, but not quite, because I've got this h stuck on the left hand side there. So let's get rid of the h, move it over to the right. So we'll now multiply the last equation on the right by the inverse of h. So this time we get kh to the minus 1. Now, I claim that what's on the right-hand side of that equation, kh to the minus 1, is an element of the subgroup h. So the reason for this is that h is in h. So h inverse is in h, because h was a subgroup, so it is closed under taking inverses. So kh to the minus 1 is in h, because h is a subgroup, so it's closed under taking products. Okay, what have we got then? We've got y inverse x is an element of H. And by the Coset equality lemma, xh equals yh. Okay, let's look at our last result then for this video, which is about the size of a coset. What it says is that the size of a coset of H, whether a left or a right coset, is equal to the size of H. And this actually is really easy to do. So I will expand a little bit on the proof here. The proof says that there is a map from H to the left coset GH given by left multiplication by G. And that is a bijection because it has an inverse, which is left multiplication by G to the minus 1. So since it's a bijection, those sets have the same size. Now that's just for the case of left cosets, but the argument for right cosets will be exactly the same. So let's just quickly expand on this a little bit. What's going on here? Mg is, I'll make that look a little bit more like a subgroup, like a subscript. Mg is the function from H to G. H, and Mg of an element of H is G times that element of H. And this is genuinely a function that goes from the subgroup H to the coset G times H, because this is an element of GH for sure by the definition of the left coset. On the other hand, you can also define Mg to the minus 1. M is short for multiplication, and it goes from GH to H. And you can define that by saying, well, Mg inverse of an element of the coset, so let's just use X to refer to an element of the coset, that's defined to be G inverse times X. And that really is an element of H. And the reason it's an element of H is that actually X is equal to GK for some K in H. So G to the minus 1x is equal to G to the minus 1g. K is equal to K again, and that really is in H. So this Mg to the minus 1 really does provide us with a function from GH to H. And of course these things are inverses, because if you do Mg of Mg to the minus 1 of x, what do you get? You get Mg of G inverse x, and that's G inverse x, which is x again. So this composition, Mg composed with Mg inverse, is the identity on GH, because it's an x to x, no matter what x was. And similarly, the composition the other way around is the identity on H. Therefore, both compositions of the identity, these maps are inverses of one another. So they're invertible, so they're bijections, and that means their domain and codomain have the same size. So the coset of H has the same size as H. We're going to see why this is so useful in our next video.